Hello, organickers. What we're going to do today is continue on with acid and base theory, particularly as applied to organic chemistry. So we are still in our chapter 2 in our textbook, and we are going to go ahead and talk about the strength of acids and bases. Again, particularly how this applies to organic chemistry. So let me share my screen. So what we have is a couple of ways to tell that how strong acids and bases are. One is the extent of dissociation. So a strong acid is something that reacts completely or almost completely to form H3O plus ions. So basically, if HCl dissociates in water, ionizes in water, I don't have any intact HCl molecules. What I do have is all of the HCl that was present in the solution has now ionized to form H3O plus and Cl minus ions. A strong base is the same sort of principle. The strong base is one that reacts completely or almost completely to form these OH minus ions. So again, these are those bases which, when dissolved in water, are going to completely dissociate to form the cation and OH minus ion. So I don't have any of the solid left. It's basically soluble in water, and I get hydroxide ions present. So this is sort of the important part of all of this. You need to remember these 6 acids because these are the strong acids. Now, the idea is if I'm not strong, I'm weak. So any other acid except for these 6 will be a weak acid. So if my acid is an HCl or HBr or HI or HNO3 or H2SO4 or HClO4, it is a weak acid. These are strong bases. And basically what you're going to see is these are from group 1A and 2A metals. So lithium, sodium, potassium, and then barium. Those will fully dissociate in water in order to form the cation, the metal cation, and then OH minus. Now, a weak acid is a substance that only partially dissociates or ionizes in water. So acetic acid is a weak acid. What this means is I have a very low concentration of the conjugate base and the conjugate acid. Most of the acetic acid that is present in the solution is intact and is protonated. So for example, out of every 1,000 molecules of acetic acid that are present, only 4 are actually found in this conjugate base form. So the vast majority of the acetic acid molecules are intact acid molecules and not ionized or dissociated. So that's how I think about a weak acid. Weak bases are thought of, again, along those same principles. Weak bases only partially dissociate in order to produce OH minus ions. Now, ammonia, which is NH3, is a very weak base. It actually produces OH minus ions, by reacting with water, as we've seen, to form the ammonium ion and the OH minus. Again, this is present in the largest majority. The NH4 plus and the OH minus ions are going to be just a small fraction of the material in the solution. Most of it is going to be intact ammonia. Now, I can quantify acidity by using numerical data. Again, whether you've seen this or not depends on what type of prereq that you took in order to get placed in this class. Again, if you took a lower level class that covers more topics in a semester, you may have been exposed to this. For those of you who took Chem 1, this is not actually discussed until you get into Chem 2. Ka is a value that can be measured and calculated. It is called the acid dissociation constant of an acid when that acid is dissolved in water. It is the measurement of the acid strength when water is the base. So this is going to be my acid, and this is going to be my base. This sets up an equilibrium situation where I can actually calculate the equilibrium constant, which is this K equilibrium. Notice here, if you've ever paid attention and learned this material, I have the molar concentration of the H3O plus ion times the molar concentration of the A minus cation or anion divided by the product of the molar concentration of the acid times the molar concentration of water. Now this is a liquid and it's present in large amounts. I think pure water is something like 55 molar. So to go from the K equilibrium to the Ka, notice this has the concentration of water already accounted for. Typically, in equilibrium expressions, you do not include solids, liquids, and gases. It just, or you don't not include solids and liquids, and it just applies to gases and aqueous solutions. So this is the equilibrium expression that will give us Ka values. Now, I'm not going to have you derive these. This is something that you would do in your general chemistry course. What you have to do is know how to use them. So we are going to compare Ka values in order to assess strength of acids. Think about this. These are my ionized components, and that's the numerator. This is my intact acid, and that's my denominator. Based on what we just talked about, where strong acids are going to fully ionize or dissociate to A minus and H3O plus, that means the concentration of those ions is going to be much greater than the concentration of the intact acid, because basically that's going to be a really small number, or 0. So if the acid is strong, my Ka is going to be large. If my Ka, or if my acid is weak, my denominator is going to be a much larger number relative to the concentration of my ions, because it does only partially dissociates or ionizes. So my weak acids, because my denominator is going to be much larger than the H3O plus and the A minus, is going to be a very small number. So I can actually look at the value of Ka. Ka values are tabulated. They are going to be in any chemical resource that you might find. I'm sure you can Google tables of Ka data. And basically, they're going to range from 10 to the minus 50 to 10 to the 10th. So this is going to be my very strong range, and this is going to be my very weak range. So because of this large variance and because of these large exponents, the sizes of these numbers, they tend to be either very small or very big, are hard to work with. So we're going to work with another parameter, which is called pKa. pKa is the negative of the log of the Ka. So now I've taken those scientific notation Ka values, and I've gotten pKa values, which are minus 10 to 50. This trend now, because it's a logarithmic scale, has reversed though. So the lower the pKa, the stronger the acid. So basically, as Ka increases, acid strength increases and pKa decreases. This is going to be a very important relationship. Large Kas give me small pKas, and that is a relationship that I'm going to actually look at and to assess how acidic a particular molecule is. Here is a chart, and I have given you a chart that I prefer, a common pKa value for organic chemistry. That I posted that in the module for this particular section. Remember, this is logarithmic, so each pKa unit represents an order of magnitude or a power of 10. These charts will give you the acid as well as the conjugate base, and then the pKa values can be assessed in order to compare acidity. So for example, using this knowledge, H2SO4 has got a pKa of -9, very, very low number, very, very strong acid. And it's going to be 100 times stronger than the pKa for HCl, because my pKa there is -7. So I have 2 log units, 10 times 10, and that's giving me that 100 times stronger value. I can also quantify basicity, and I can use pKa values for the acid to compare the strength of the conjugate bases. And that's because of this principle right here. The stronger an acid, the weaker its conjugate base. So H2SO4, which is an extremely strong acid with a -9 value for pKa, is actually that conjugate base, HSO4 minus, the bisulfate, is a very weak base. And then look here, an alkane, if I think about an alkane as having an acidic hydrogen, this is a very large number. So this is an extremely weak acid. Because of that, this anion here, when I take away that hydrogen and leave that lone pair, which is my negative charge, this alkyl anion is the strongest base on this chart. All of this information is really important for organic chemists to know. So here's an example. Using pKa, what is the strongest acid? So what I want to be able to do is use my pKa chart. And just to show you, I am going to have ethanol. This is acetylene. This is ammonia. and this is acetic acid. And this is, it doesn't have a common name. But I'm looking at how easy it is to pull off these hydrogens when this molecule acts as an acid. And if I look at my pKa chart, this is the one that I actually gave you. What I'm going to look at is I'm going to look for numbers that correspond to what I had before. So notice here's acetylene, which has a pKa of 26. So when I go back to this chart, this is going to have a pKa of 26. So if I put my pKa values here. Then if I look at ethanol, I'm going to look for that. And here's my ethanol. This has a pKa of 17. So when I look at this particular number, this is going to be 17. Then when I look for ammonia, using that as an acid, I'm going to see that ammonia has a pKa of 36. So now I look back at my chart. Ammonia is going to have a pKa of 36. I'm also still looking for acetic acid and then this dicarbonyl compound. So when I look on my pKa chart, I'm going to look for, here's my dicarbonyl compound, which is 9.2. And then here's acetic, that's not acetic acid. Here's acetic acid, which is 4.8. So my acetic acid is 4.8 and my dicarbonyl is 9.2. So when I go back to this question, this is 9.2 and this is 4.8. Well, remember, the lower the pKa, the stronger the acid. So I'm going to just look at acetic acid is the strongest acid on this chart. And then I have my dicarbonyl compound. And then I have my ethanol. And then I have my acetylene. And then I have my ammonia. And that's because this is the lowest pKa. Here's the next pKa, then 17, then 26, then 36. So this is my order of acidity, which means this acetic acid is going to be the strongest acid. Now, how can I do this where I'm looking at using pKa to find the strongest base? Well, what I want to do is think about the corresponding acid to these. I need to think about H3O plus. I need to think about HBr. I need to think about H4 plus. I need to think about H2O, and I need to think about alkanes. So when I do this, I need to be able to use my corresponding pKa chart, and then I'm going to correspond again to see which is the strongest acid. This trend, the strongest acid is going to be the weakest base. The strongest base is going to be the weakest acid. So I have to look at these pKa values in order to go ahead and make this assessment. So I'm going to look at my pKa chart. And I'm going to erase these guys because now I'm going to use different numbers. HBr is not in here, but it's probably somewhere between here. So I'm going to call it a -8. So if I look here, I'm going to give this a -8 as a pKa. I'm still looking at ammonium, hydronium, and just plain water, as well as an alkane. So when I go back to my pKa chart, notice my alkane is going to be right around my 50 mark. My water is going to be right around 15.7. So when I look back at this, water is going to be 15.7. My alkane is going to be 49. I still have ammonium and hydronium. So when I look at this, ammonium is going to be 9.4 and hydronium is going to be -1.7. So when I look at these, I have
Mom, I need an extra one day.
I have a 9.4 and I have a I forgot what I was just saying. I have a 9.4 and a -1.7. So this is what I'm going to do here, a 9.4 and a -1.7. So this is actually my strongest acid, and this is going to be my weakest acid. Remember, my strongest acid is correlating to my weakest base, and my weakest acid is going to correlate to my strongest base. So here is what I'm going to give you for your strongest base, or your strongest base. And that's because the pKa is indicating that that is the weakest acid. All right, at this moment, I'm going to come back and we'll be able to predict equilibrium. I will see you in a bit.